All right, so in this video, we're going to walk through an example of finding and simplifying the difference quotient for a function that has a radical in it. Now, the cubic examples, cube root examples are a little bit more complicated than the square root examples. You rarely get asked to do cube root examples, but we're going to stick with the square root example here. Now, there are some special tricks that you have to apply in order to get these to simplify. Again, our goal is to get that h out of the denominator ultimately. And so we're going to go through tricks that are specific to the radical case. Now, again, recall, we're going to break this down into our various pieces and apply our function notation. F of x plus h gets replaced in our function where x is. So this is going to become the square root of 4x plus h minus 7. Or you could write it, if you wanted to, 4x plus 4h minus 7. Again, this doesn't really help much, but if you want to get rid of the parentheses like that, you can. Now we're going to combine this with our minus f of x. So f of x plus h minus f of x. And so we'll have our square root 4x plus 4h minus 7 minus the square root of 4x minus 7. Now, initially, this seems like there's not going to be a lot of simplifying that we can do. How are we going to get rid of this h in the denominator? Because ultimately, that's really what we want, especially when we get to calculus. We're going to need to get rid of that h in the denominator and make it go away. Well, the trick that we're going to apply in order to accomplish this is going to be to multiply by the conjugate. So typically when we rationalize fractions, we're trying to get the radicals out of the denominator. But in this case, we're actually going to try to get the radicals into the denominator because that is what we need to do in order to get rid of that h. Now, in order to do that, if you remember rationalizing, dealing with square roots, what we're going to multiply by is this same expression over itself, but we're going to flip the sign between the two square roots. Now, the reason for this has to do with the difference of squares formula. We want to be able to take advantage of that difference of squares formula and make sure that since the signs on the inside are different, that middle term is going to cancel out. So recall if we have a plus b and a minus b, we get a squared minus ab plus ab minus b squared. And so all that's left is the squaring on both ends. And that's what we want to do. That's what's going to get rid of this radical in the numerator. Because this expression is a and this expression is b. So just to kind of make clear what we're doing here, this is our a expression, and then we're going to square it. And then our b expression is this guy. And we're also going to square it, a squared minus b squared. In the denominator, we're still going to have h and this entire expression. Don't bother distributing because you'll just have to factor the h back out again. Leave it alone. Now, when we square a square root, what happens is we end up with just the thing under the square root. So this becomes 4x plus 4h minus 7 minus, and in parentheses, 4x minus 7. Denominator did not change. And if I distribute that minus sign, I'm going to get 4x plus 4h minus 7 minus 4x plus 7. And so what's going to cancel? 4x and minus 4x and negative 7 and positive 7, all gone. And so what are we going to be left with? Well, in the numerator, it's going to be 4h. And in the denominator, it's going to be this whole thing. But I've now got h and h. And so those can cancel. And I'm going to be left with the h is going to disappear. There we go. Now, again, in algebra, this may seem like this hasn't really helped that much. How is this that much better than before? Well, the way that it's better is that in the difference quotient, this is the difference between 2 points on a function. And what we're interested in is what happens to the slope between those 2 points, because this is the slope formula. What happens as those points get closer and closer together? In fact, what happens when they get all the way and they become the same point? So the difference between them is 0. And we can't evaluate this expression if h is 0 because it's in the denominator. We can't divide by 0. So we're doing all of this algebra in order to get that 0 potentially out of the denominator, and then we can go ahead and we can evaluate the thing now for any value of h, as long as it's not so big that it takes us off the function curve.